Can you guys hear us? Okay, thank you. Thanks for joining us. So first of all, some correction. I'm not lead for any AI strategy. Sorry about that. It was on LinkedIn. I put it 5 years ago, and it just stayed. I should change it. I lead a small co-design partnerships team at NVIDIA. So we work with some of our partners who are on the frontier to help influence the design decisions for hardware and software roadmap. So having said that, we have 4 awesome panelists on the very interesting and continuously evolving topic of reinforcement learning. So I would like for you to introduce yourself, your journey with reinforcement learning, and the framing for this context is it's changing day by day, especially in LLM space, and we are trying to monitor how things progress. There won't be any Q&A at the end, I'm sorry, but I think it will be interesting. So Linden, you want to start, what was your journey with reinforcement learning and how you landed where you are and what you're doing with it right now?
Cool. Thanks. I can get us started. So my name is Linden. I'm one of the co-founders of Applied Compute. A lot of what we do is we help enterprises build agent workforces, and a kind of uncompromising belief that we have is that the vector for all kind of economic development via AI will happen within businesses. And so we embed with them very closely, and we help kind of understand their problems to work towards automation in that regard. A big component of that is having access to specialized intelligence. And so as a result, a really important part of that is RL, where we take companies' proprietary data, transform it into environments and data points that we can train on, and eventually use that as the starting point from which we can create sovereign-owned models that are state-of-the-art at the tasks that our customers care about. Prior to this, I think a lot of the conviction for this came from what we were doing at OpenAI. So my co-founders, Rhythm, Yash, and I were all working with, JT, Liam, and Yuchen here on similar problems back then, where a lot of the conviction came from this paradigm of having existing models with a lot of really great capabilities that we'll learn during pre-training that we could draw out and create state-of-the-art agents trained end-to-end from. So yeah, that's how I got started.
Yeah. And I should have mentioned, you will hear a lot of references to each other because they all have been at OpenAI at some point of time. So Yuchen.
Yeah, hi, I'm Yuchen. I'm one of the co-founders in Humans and what we're doing is basically trying to come up with the next RL paradigms that will make model learn and interact with human and with a lot of humans. So what we think is a lot of training paradigms focus on trying to make the model smarter and help people do a lot of things. But in the same time, people are not having the models that constantly learning with humans and interacting with humans along a really, really long period of time and with a lot of people, inside of a community. So that's why we come across these journeys of we want to build models that truly understand and interact with people. And again, I also came from, my background is started from robotics, and then I work on recommendation using RL for engaging users, and also in OpenAI I work on basically post-training model behavior, and then I moved to XAI working on user preference and agentic models. So we think the next journey of RL will be help people understanding each other's and working with people.
Awesome, thank you. Jerry.
Hello, my name is Jerry. I've worked until very recently for the last 7 years at OpenAI. I joined this company because I got really smitten by the results from DeepMind researcher combining deep neural networks and reinforcement learning together. I saw those agents trained on Atari, and I wanted to find a team of people that can do this together with, and can research this RL thing together. And I feel like I lived and I worked for the first wave of RL when you train on games. I trained on robots. We trained things like StarCraft and Go at that time, and RL was pretty exciting for a while. And me, together with a lot of other researchers, we got a little bit sad when RL kind of took a little bit of a back burner in the world of AI research, where transformers and large language models started to work. And I always believed, in a really deep level as a researcher, that learning from experience and learning by trial and error is a necessary element on the path to AGI. I always was there thinking, how do we do that? And I was lucky enough and persistent enough to be at the right time and place in history to lead the team that put RL back on the map, specifically scaling up and the large-scale reinforcement learning that we are doing. I led the work on the reasoning models at OpenAI, on the O1 model, O3, and a lot of the work that is fueling all the models that we use and love. And I think like to me it has been an inflection point in how we train models, how we do large-scale modeling in some way, because it's a very different algorithm how we are training models today than 2 years ago, and in some way those are different workloads with different objectives, with different data sets, and we are in a very, very different world that we have been. I don't think the innovation has finished, but everyone is thinking and everyone is doing RL these days.
Yeah, thanks for the whole end-to-end. Liam.
Hi, and my name is Fedus. I'm one of the co-founders of Periodic Labs. Our goal is to create an AI scientist. The way we think we get there is you have to do science. We don't think that comes from just reading papers, from reading textbooks. We think it's very necessary to do reinforcement learning against the physical environment. So what we're building is systems that are carrying out semi-autonomous experiments and learning from the environment. I had the joy to work with everyone up here. And over the course of my time at OpenAI, we just saw reinforcement learning so successfully deployed to all of these different products, and had a very similar experience to Jerry, where my first experience with RL was in Atari. DeepMind was like pushing these frontiers forward. And the models at the time were just these little 3-layer convnets and seeing really nice behavior. But then putting this on top of really strong pre-trained models unlocked things like ChatGPT. And I think we saw over time that if you have good reward signals, if you have something verifiable, you can basically always make the number go up. You can always scale. And that's what gave us the hope to go out and actually show that we can do reinforcement learning against the physical environment. We think ultimately that that's the environment to optimize against.
Awesome. Thank you. So since like all of you mentioned scale to some degree, like what does scaling in RL mean? So with pre-training, we understand this, we have laws and we have rules and everything. And then till a year back, there was this thing going on, scaling has hit its limits. And then people are talking like scaling is limitless. So like if you wanna start, Liam, like what does it mean for you, scaling?
So, I mean, quite simply, you're just throwing more compute against these different environments.
Okay.
So that you can scale the number of environments, you can scale the number of attempts against these environments.
Yeah.
You can scale how much thinking, what kind of tools you're applying for each of the tasks.
Okay.
And also just the models have become larger.
Okay.
And pre-training has been guided by very nice scaling properties. I think it's been augmented and guided by very like high signal to noise evals. I think RL post-training can be a little bit noisier, and it can sometimes be a little bit more difficult to create as smooth scaling properties. So in the early days, there was definitely a lot of vibe-based RL. But yeah, I think it's just putting a huge amount of compute along these different axes.
Okay. And would that be because you're handling all these different verticals in terms of physical sciences, or would the definition of scaling for RL change for someone else? Is it just compute?
Well, the number of environments is a key part. And so for us, what we're building up are data, and we have access to labs to give access to new types of environments that simply don't exist anywhere else.
Okay.
So in addition to us thinking about scaling up the traditional compute infrastructure to do pre-training, to do reinforcement learning, we're also thinking about the physical infrastructure of labs. And we think that this is going to be the key to unlock scientific discoveries.
Okay. Thank you. So Linden, like you work with a lot of partners, your own partners, and you are scaling things in your own capacity for a bunch of different of them. Like, how do you think about it?
Yeah, I think, to kind of continue off of what Liam was saying, I think when we look at the previous generation of pre-training scaling, it was just kind of like there's this blob of compute, we measure it in some unit of flops, and then we figure out how to actually allocate it at training time. And I think the nice property of pre-training is that the kind of optimal data mixture and also number of parameters kind of smoothly falls out of that. I think we aren't quite in the place persuasive RL, well, that's as well understood. And so we're still kind of figuring out the right scaling recipes to do this. And I think for us, when we scale for our enterprise customers, a lot of it is just figuring out the right amount of, the right amount of compute that you can actually spend on a problem. And for us, it's less so scaling the amount of like training compute. And, as Jensen said this morning, the new workload that we're spending a lot of time focusing on is spending time optimizing language model inference, where in a lot of our cases, the problems that our customers care about aren't necessarily in the distribution of what the large labs are training on. And so it requires a lot more attempts to actually solve the problem and a lot more like thought process when you're actually going about solving it too. And so for us, a lot of it is just scaling, not necessarily the number of environments that we train on, because, within enterprises, finding a structured environment is actually quite tricky, but it's in a limited data regime. How do you actually get enough learning signal out of the data points that you have in order to, learn properly on the task? And so we think of that primarily in terms of how much compute we're allocating towards language model inference.
Awesome, thanks. So Yuchen and Jerry, do you have any comments on top of that?
Yeah, I think on top of all the environment, agent, and data scaling, I think what we find most useful is people are constantly interacting with other people, and people are extremely good at navigating ambiguities and a lot of uncertainty in the environment. So for us, it's more about scaling over long horizon. How do you get more delayed reward, learn from all these delayed reward? How do you actually build up systems that is learning from a lot of interactions with a lot of people and agents in the environment, and as well as the scaling come from also be able to make the model truly learn from all these unseen and uncertain setups, instead of there might be a lot of verifiable reward we can learn from, but for us it's a lot of unknowns on the metric and unverifiable reward over the time. Yeah.
Awesome. So Jerry, if I were to you should answer the same question, but I was also wondering, since you mentioned that at OpenAI, you saw the whole gamut of it, like robotics, and for it to take a backseat, then come back again, and you tried a bunch of different verticals, which is spinning off these companies now. So where would you see things break, like the evals, or how do you even measure if scaling is breaking or blocked?
Usually how when people are training a model, breaking scaling means the things don't improve during your training run. And it probably happened to everyone who ever trained a model. You train a model and has some curve, and suddenly it stops. There are sometimes completely failed training runs where things go down and just plummet. And there are the ones where things stay, or at least improve more slowly than you would expect. We, in deep learning practitioners, we do expect some things to extrapolate, and we usually have some expectations of how good of a training run will be if we finish. And I don't think, probably a few times doing completely new experimental stuff, it has happened that things turned out better than people expected, but most of the time either they end up where you expect or slightly worse, and the question is how much worse based on that. So usually scalability is how well you can hit your goals, your targets that you set when you start this journey of scaling. Okay.
And maybe with you, I will try to get into a little bit of researchy side of things as well, if that's okay. So now folks are talking about limitless scaling. It's is that infinite amount of compute, which is amazing for NVIDIA? Or is it something different?
I very much believe in that. Yeah. The learning shouldn't end, and we think how humans learn or how human civilization learns. Right. There's always something more to figure out. There's always something more to find. And there's definitely tons of learning signal in the world, and the limit on places like what Liam does, figuring out new science, figuring out new materials. There are so many things to learn and to figure out that there isn't any limit. That there's a question is our recipe today good enough to be able to scale it infinitely? And there are clearly still some bottlenecks. Things are at least shaky. Training models is a little bit of like a work where you have to put a lot of elbow grease and then tweak things around and try to set them just right so that they train. But we've been even thinking about how the current run of scaling up reinforcement learning is not very old. How many great models have been trained very successful, and the agents that we have, how many things they can do for us very reliably. It's pretty amazing of where we got on it so far.
Yeah. So if we were to bring that back to you, like AI for science, or do you experience things change if you're doing, say, material science, or you're doing cooling, or you're doing genome sequencing?
Well, maybe one interesting thing is what is the RL environment? So you could have a very simple environment, like what is 2 + 2? You know the ground truth is 4, so you can do a lot of optimization against that. In that case, you probably don't need a lot of chain of thought, a lot of tool use, but you can construct harder, verifiable problems. When we carry out an experiment, it's not that we get one bit of information from that experiment. It's not like success or it didn't work, or it's not even a continuous reward problem. There's a huge amount of data associated with each of these experiments. I mean, to Jerry's point about there's always more to learn. And so if you have a system at the frontier of its knowledge, you're directing experiments where there's just very limited scientific data, you're trying to discover new things, you can also begin to construct environments that are trying to predict various properties of this. So in our case, we're doing physics experiments, materials discovery, and we can try to predict aspects, various aspects of the experiment. So that's one way we're thinking about it.
Awesome. So,
and then maybe another interesting aspect too is simply just the latency of the reward functions. In the early days when we were building ChatGPT, the reward function was just classic RLHF, and the reward function was basically a forward pass through a neural net. And so hundreds of milliseconds, second, it's a fairly quick thing to do a pass, which is, how's this completion? And if you look at some of the state-of-the-art models, I mean, now you see like reasoning traces and combined with like grading, like getting closer towards an hour.
Interesting.
And hour plus. And at periodic, we're thinking about the next order of magnitude. And it seems daunting, but I think just seeing this kind of trajectory over the last few years, I think this is definitely going to be in scope. But then it kind of gets into learning more sample in like being very sample efficient in that, dealing with credit assignment, dealing with just like very sparse rewards. But making progress.
Interesting. Okay. So this is something that you still control, like it's still within your periodics regime that you decided to train this, you decided to train this. Like for someone like you, Linden, that I saw your latest one, DoorDash, for example. Like how do you tackle that problem end to end for different customers and different verticals? Like what are the problems you run into that?
Yeah, for sure. So on the topic of kind of I think there's the aspect of how do you actually figure out what the reward signal is, and then the issues kind of downstream of that, which is once you have a verifiable signal, there's all sorts of different failure domains that happen after that. So the way that we typically run engagements is I think, to Liam's point earlier, there's a lot of really nice verifiable properties of math and programming. And when you kind of get in the real world with enterprises, a lot of those assumptions kind of go away because oftentimes in domain experts' heads, they have some idea about how they complete a problem. There are other experts which might not agree with that. And so figuring out what the metric to optimize is really challenging. The nice property of RL is once you figure out which hill to climb, you can kind of throw arbitrary amounts of compute at it, which I guess is great for NVIDIA. But prior to that, it's really challenging to do that. And so what we do typically on the ground is we'll work directly with kind of subject matter experts or technical teams to figure out what it is they care about. It's maybe some downstream metric with a lot of business impact, or it's potentially something else. Like, for example, the cost of running a frontier model is far too high. And so what they want to do is they want to have specific completion within a latency budget. And we can just, kind of arbitrarily pack those additional terms onto the reward to make sure that models for example, think faster or emit responses a lot faster than usual. And so that's typically how we run it originally, and it's a lot of iteration. So, you'll scale the first iteration of compute. You'll realize that there's all these different failure domains. Like there are maybe cases of reward hacking where, for example, there are particular cases that you had a blind side to that weren't in your original that weren't in the original training data. There are cases maybe where you didn't mock the environment properly. For example, DoorDash has a very specific way of doing things, and if we kind of deviate away from that, it kind of results in degradation of the model relative to what they care about. And so, I think a lot of that is just really rigorous engineering to make sure that what hill we're climbing is fully aligned with the downstream business impact they care about.
Yeah, makes sense. Yuchen, you're still very much in. I didn't mean to say that everything is in your control. I was thinking about it when I asked the question. But still, it's a little bit of variability when you're dealing with outside forces and partners. So coming back to you, right? You're also like building the product right now.
Yeah, we're building product for both like consumer and business.
Yeah.
And I think the core for like basically we cannot scaling like infinitely is that like verifiable environment is like challenging itself, but on the other side, there's also like a lot of these unverifiable environment, and there's like when people are in the environment, it's actually to introduce more noise and introduce more dynamics. And people have to work with each other to achieve like great scientific discoveries. And people have to work with each other to build software stack together and building product and building like very customized like different frontiers for people to actually leverage. So I think like fundamental questions we actually cares about is like how general the model's learning is and how can it actually generalize from just like doing simple math problems from the beginning, like 2+2, all the way to like solve like very complicated problems with like very dynamic environment and basically have the capabilities of build up its learnings over time and be able to work with a lot of group of people, figure out what they want over the time. Yeah.
Okay, cool. So
What actually just kind of like reminded of a couple of these points. One thing that we think a lot about in like the reward construction seen many times is if the policy under like the argmax of that reward is not what you want and you throw a lot of compute against it, you're going to have a bad time.
Yeah.
And I think this is, you know, very often it's like not super concrete and these like misspecifications when you then optimize against it can really cause like a lot of issues. Like the model doesn't really know what you intend. It just is trying to find the highest number.
So is that something that can be automated away at some point or still very much a craft and a skill?
I think it you know kind of requires a lot of the craft of engineering the right reward function. I think is very challenging. I think sorting, you know, I know there's a lot of stuff with kind of like automated researchers these days, but I think that's only valuable insofar as you actually know what the objective is. And so I think, you know, to the extent that we still know our preferences, I think it's you know, I think it's really important that you actually do that. And yeah, to Liam's point everywhere, I think one thing we've been bitten by so many times is that models will just try to get optimization signal from like literally everywhere, and there's so many interesting ways that in which that can fail. Like when I think about when I used to work on kind of pre-training systems, the library itself was kind of self-contained. It was literally just like your Megatron optimization stack. But these days it hits like all different types of things. It'll hit like external APIs for maybe grading an outcome. It'll maybe hit like, you know, a lab in the case of doing AI science. You know, in our case, we like mock customer environments. And if any one of those portions fails, then you can get the, you know, sadness that Jerry was talking about where your reward will just crash. Like I remember there was a couple of nights ago, we like hit our OpenAI rate limits. Then all of a sudden the model just kind of kept getting like an anvil dropped on its head where it's like everything it would be wrong because the API response would always just be an error. So there's just kind of subtle things like that we've just been bitten by many times as well. To go back to the, you know, question of obstacles at scale.
Yeah, no, that's helpful. Thank you. So if I like coming to you, like I always pivoted back to research. So what's researchy in this optimization for you? Like, so you were mentioning like right now it's still pre-training and inference, pre-training and RL, and you, if you don't mind sharing, you're talking about merging training and inference completely.
Yes.
How do things get more interesting there?
I think there are many challenges ahead in terms of reinforcement learning research, and I think combining pre-training and RL into a single algorithm is something that we as humanity, we as deep learning researchers need to figure out. Currently, we have this two-stage research process, which honestly is a bit awkward and a bit weird. We need to like understand a lot of world knowledge into our models, so that we can kickstart the RL process, and the RL process teaches us what do we do with that world knowledge and how do we use the things that we have seen during pre-training to achieve goals and outcomes that we want to do. But at the same time, this process kind of limits like what the model can do going forward, what the model can do online. And at some moment, if you really find the algorithm that can give you both world knowledge and like behavior goal seeking at the same time, you suddenly can start like applying it at test time. You can apply it in like Linden said, like we need to currently mock environments and build like fake representations of the world. We train them all in a lab and then we deploy them to the world where they are essentially static and not learning anything. But we wouldn't have to mock anything if we can actually train on the real systems. If we can actually train where the customers are and where the real world need for intelligence is, it's like very clearly for every researcher something that will happen at some moment. And I think like splitting training and inference workloads is only only so far. Only at this moment, this is how we do those things. But the models need to be adapting, just like intelligence is about adapting to every situation you find and finding new insights and finding better ways to solve problem every time you are doing it. Currently the models are really great at kind of almost everything, but at nothing they are truly at the expert level. On everything there's a human that is kind of better than this model, because humans have worked on every human has worked on some domain of their expertise for 10 years, 20 years, and the models still don't have this type of depth of expertise in a domain, and only that spending that 12, 20 years on this domain can get them there.
So what would the how would the platform change? How would the hardware engineering, systems engineering, what would the complications you will encounter there? How would that meaningfully change for you?
There are in terms of systems, if you are asking about that, I think at some moment we'll have much more personalized models. It will not be one model for the whole world, but people will have their own models which are really good at what you do and what you care about. And there are probably some shared learnings. But if you think about the current models, even how mixture of experts work, there are probably experts there describing some medieval war in Europe that's almost no one else asking about, but the model knows all that, and that knowledge is stored there. Do I whenever I am trying to discover new science, or whenever I'm solving deep learning problems, do I need to know about the medieval wars in Europe? It's a really great thing, but those are experts that are probably not very active for me and not very important. I think models that adapt to what you are doing and are really great at that thing. This is like the journey of first pre-training, then reinforcement learning is already going into that direction. We have this notion of jagged intelligence. The main downside of jagged intelligence is that it's jagged not necessarily in the way I want. Yeah. Only making it jagged in the right way is actually training on the things I need.
Thank you. And for you, Liam, just shifting the same question to you, at some point of time, you see yourself getting to continual learning, or what's working right now and how meaningful it will change what you're doing right now?
I think looking towards the future of this, I think this disconnect of in the old days we pre-train and then there's a little bit of RL on top, and then there was a lot of RL on top. I think it's definitely shifting. One aspect that's changing is you have a system that can produce data for itself. And so one source of data for itself is just it's out in the world, it's exploring the frontier of its knowledge. Those types of traces can be useful for just new sources of data. And so then you can kind of see it's kind of bringing it a little bit closer, these two disparate things.
Right. So
and then extreme would be it's just a fully continual learning. So so I see the vision of it. But I think there's hurdles about just so much of our infrastructure and tooling has kind of been built up with this paradigm in mind. So it kind of ossifies the type of research you do.
Yeah. So, one thing that Jerry mentioned, and I'm hearing it from quite a few other folks, I would say, or startups as well, is that eventually most of the consumption is going to shift to the personal devices. So even you probably won't have a laptop in the laptop form that we are seeing right now. So how much of that applies to the fields you are working in?
We might, depending on some maybe more data sensitive environments, we might throw compute really close to specific machinery. So you can just go up to a little black box and talk to that machine, and it's just completely insulated. But generally in this space of scientific discovery, we're
different.
It's a different application.
Awesome. So the same question applies for you. at some point, like everything is tightly tailor-made to how things are right now. Like the infrastructure, the data centers, even the hardware planning that's going on is, okay, you have a base model and then you do some things on top of it. But how do the new business cases emerge and you take care of it as things start? I'm not saying that, but suppose one of these guys starts yet another company and cracks continual learning. Like, how does that impact, or how do you plan for something like that?
Yeah, I'm so glad you asked that. So I think a lot of the research program that we have at Applied Compute is actually is dedicated towards solving the kind of continuous learning problem. And I kind of view ourselves as, kind of well positioned to do so, because one of the things that I think we've been really excited about as a company is now that our models are deployed, they produce a lot of data on how they're actually performing real time in production. And I think the central question for us this year from a research perspective is not only just scaling up existing RL systems, but now that you have an abundant, almost like limitless source of traces from production, how can you find out whatever sparse nuggets there are of reward signal there to make your model ultimately better? And so this is kind of like how we'll close the data flywheel here. And so an important component of that will just be, okay, we need to instrument a ton of observability and telemetry into how models are performing, take the ones in which there were surprising results or cases that we were totally blindsided to during training, and then retrain them to make them a lot better. And so I think figuring out kind of like how we close that loop is something that we're actively experimenting on, especially for the enterprises in which we've deployed these kind of specific intelligences for them. I think the other thing as well, just to go back to your idea of kind of systems and the bottlenecks behind scaling too, is I think there's something really exciting and compelling about all the different hardware advances that are happening right now, where it doesn't really need to be on device. Like we can train like many, like hundreds of billions of parameters of MOEs very quickly now. And now that we have things like advances in Rubin and the generations that are happening beyond that, the rate at which you can produce weight updates is just an order of magnitude that you could have before. And so for us, I think the recipe will be, first of all, identifying like an adequate volume of data to train on, and then just pumping it through all the modern kind of like NVIDIA rack scale systems to get weight updates even on the order of magnitude of like of days or even a couple of hours, where you can constantly be training these systems. And so that's kind of how continuous learning works for us. If there's another startup that works on cracking it, I think we'll be competitive with them. But we're just figuring out ways in which we can leverage all the information we're getting at deployment time to make our models way better over time.
That's awesome. Thanks. So if I come to you, like whenever we spoke, you referred quite a lot to memory.
Yeah.
With respect to scaling the systems. Like, I would like to hear more, like, are you working on that right now? Or like, what's your past experience, how that scales, or how it needs to evolve?
Thanks for the question. I worked with Liam on the ChatGPT user memory 2 years ago. I think it's kind of like an echo back to the previous continual learning problems as well, is like the model like goes through pre-training, set up some priors, learn how to like echo on things, like basically repeating on things. But the model doesn't fully understand what is behind the door and why things happens that way. It doesn't rationalize things like a human does. And also, I guess like all these, like people are saying like nowadays, like we're basically exhaust all the pre-training data, but actually there's a lot of way richer signals that is in all these data that people generated over so many years. And we're just not learning all the fundamentals and all the like general capabilities of learn to learn from it. I think like memory is like one kind of like interesting like mechanism people develop, because people cannot store all the information all in its brain, and people have to basically offload some of these and such that it can use the context in a more efficient sense. And continual learning is more kind of like, in a sense, like the model needs to figure out like what signals matters and how do I learn from it and how do I optimize my goal, and also like how do I actually figure out what is the right reward and the right goal I should learn from. Like I assume like I go back to like Liam and JT is like there's a lot of like unknowns in terms of like what goals the model should optimize itself toward. That's majority of the problems right now for kind of scaling RLs and make it constantly learning new things. Yeah.
So Liam, when I come back to you, like going back to your experience at OpenAI, you ran things at large scale. So now I'm coming to the intra question. It's like, what are the, like, if you were to have an ideal platform for scaling well, what it would look like?
Liam or Jerry.
Oh, okay, to him too.
I was like, We often get confused.
The interesting story in terms of scaling RL is that it's a very different workload that we already chatted a little bit about. It's a very different workload than scaling pre-training. Scaling pre-training is about like creating the world's most synchronized army. Imagine having like millions of soldiers that go perfectly synchronized. Everyone does the same move in a parade where they work together and walk together. And that's what you want to do when you are running a pre-training run. In terms of like RL run looks much more like guerrilla warfare. There's still this kind of like a little bit part that does like pre-training and that is like well-organized sub-army, but at the same time you have those subsystems you call, and you have inference, which can be fairly distributed and fairly different. The main question people are asking always is like, how do we make the kernels that are kind of similar to what we do in training, so we don't have that much mismatch. And the closer we can have the type of code and the type of systems that we run on inference and in training, it helps reinforcement learning a lot. But when I think how would ultimate best RL training system look like is a system that can auto-tune in some way and load balance, where maybe you can even shift the compute between inference and training depending on where it is. Because in RL workloads, basically how much load you put in which part of system, it's not some constant you start with at the beginning of the run. It depends on the behavior of your model. If your model starts thinking longer, suddenly you may need more inference. If your model calls more tools, suddenly you may need more capacity in the tool use. If the model decides to like call sub agents more, then your inference starts cascading and calling each other. And in many ways, like the reliability, the speed, the numerical precision, the interconnect, those are all things that are necessarily important. But there's this kind of question: can we build a system that is flexible to really self-tune and self-correct? Given like you cannot even predict beforehand what your RL workload will look like. It only depends on what your model is doing, and to that you need to keep adapting and keep shifting the things to really balance that out. And everyone who has run RL workload at scale knows how hard and how tricky those things are.
So it's like interplay of a lot of permutation and combinations compared to pre-training.
Yes, and the more kind of flexible and the easier the platform is to shift those things around, that's a really important thing. Everyone who has run large-scale pre-training workloads knows that like if you run some n number of GPUs and there's some failure rate, the tricky bit is, what if one fails and we need to restart the job? And a lot of work has been done at the labs to swap out the faulty GPUs as quickly as possible. And that's kind of like flexibility you need in pre-training. In terms of flexibility in RL, it's much more about like can we move stuff around during the run itself, and can we shift more resources to where they are needed versus where not.
Yeah. So it's like really advanced orchestration. How are you managing? So one thing is like if folks over here, like somebody's thinking of planning a startup, and nowadays it's fashionable, one-person company. So it sounds like more and more complicated, and you are handling different, really complicated, advanced workloads. How do you do that? How do you experience that?
A lot of pain and suffering.
Yeah.
Which I think Jensen wishes upon all of us. So
it's a good thing.
Yeah, it's a good thing.
Yeah.
It's as Jerry was saying, it's incredibly complicated. There's very complicated interplays between the machine learning, the systems, but it's difficult.
So, any lessons from the trenches?
I think good observability. I think great hardware. Just really careful debugging. Use agents abundantly. Yeah. Kind of standard advice.
So time's up. Anything last comments from either of you?
I mean, I think this is a really exciting time. I would just say that, to Liam's point earlier, I think there's so many different ways that systems can fail outside of just GPUs. And so knowing that, like, the failure domain is a lot larger than before. If you've mocked an environment, that could fail. If you have a, external API call, that could also fail as well. And so figuring that out, I think, is an important part of it. But yeah, I think it's an exciting time.
Yuchen.
Yeah.
Same.
In general, just like RL can make model learn a lot of things, but I think more interesting things come from there's a lot of interaction with the environment and with different agents. And scaling that is actually pretty complicated in terms of different model has different capabilities and constraints.
Thank you so much for joining us today. Thank you so much. Sorry, there's no Q&A, but it's up to these guys if they want to meet you and answer questions.
Thank you, everyone.